Hey everyone, let's finish example 2, where we wanted to determine whether this series in question was absolutely conditionally convergent or divergent. Well, we found using the AST, the alternating series test, that it was convergent, so the question is just, is it absolutely convergent, which is to say, does this converge, or is it conditionally convergent? Does that diverge? So let's consider that series. So looking at this, I'm focused on the n over the square root of 6n cubed part. So I think we should use, there's a little bit of finagling if you use the comparison test. You totally can use the comparison test. If you do, if you use the comp test, I'll call it, be a little careful. I think you want to do 1 over root 6 n to the 1/2. Right, and so that way this guy will be less than our term right here, that's an n over the square root of, 6n cubed minus 8. There you go. You have to be a little careful by including the root 6. Or you can just say, use the limit comparison test. And then you don't need to worry about little fine details like that. If you notice, n over the square root of n cubed really reduces to 1 over the square root of n, which is n to the 1/2, right? So let's just use that, right? So since the limit as n approaches infinity of, let's say, our term divided by this other term equals 1 over the square root of 6, right? Do you see that? Right? N times the square root of n is n to the 3/2, and that's the same degree up here as it is down here. So we're just left with 1 over root 6, which is not equal to 0 or plus or minus infinity. And since the sum from, let's say, 2 to infinity of 1 over the square root of n is a divergent p-series, our series diverges as well. So that's how you do that one. So actually, really, to answer the question, I guess I really ought to write the whole thing over again, which is -1 to the n. Maybe we'll zoom in a little bit. N over the square root of 6n cubed minus 8 is conditionally convergent. Okay. That's our answer. Right, because again, the original series converged, but the absolute value diverged. So this is an example where that alternation really did make a difference in terms of whether the series converged. Okay, let's take a look quickly at example 3 now. Determine whether this absolutely or conditionally converges or whether it diverges, right, this guy. So hopefully you could take a look at this and realize that it's a geometric series. I hope you could recognize the geometric nature of it, right? We can rewrite this let's just get this going right here. This can be rewritten as the sum from 2 to infinity of, I guess it's -6/5 times -2/5 to the n minus 1, right? I just factored out a -2/5, multiplied it by 3, right? Right? Note that this is a geometric series. So I guess what we can say, it is a geometric series with r equals negative 2/5, and so it converges to, so a over 1 minus r. You see how I did plus 2/5 minus negative 2/5? Right? And that, of course, equals negative 6/5 over 7/5, which equals negative 6/7. So a little weird, but it actually converges to a negative number. That's fine. Okay? Now, what happens if we consider the absolute value of the term? Well, hopefully you can see, similarly, I guess I should say 3 times 2/5 to the n. Well, this is just another geometric series, right? It's 6/5 times 2/5 to the n minus 1 is a geometric series with r equals 2/5. And I guess just for completeness' sake, we'll say what it converges to, but we don't need to. We actually didn't even need to include all this. I just did that to just point it out, right? So it converges to, again, I don't even need to do this, but just to refresh our memory on how to do this, right? And this equals 6/5 over 3/5, which equals 2. So the original series absolutely converges. Okay. You might notice that any convergent geometric series has to be absolutely convergent, because the restriction on r for the series to be convergent is that the absolute value of r be less than 1, be between 0 and 1.